Hello students, welcome to Inside Physics. In this session, we are going to see how an inductor behaves when it is supplied with an alternating current. An inductor, unlike a resistor, it will have some windings. An inductor is represented by symbol like this, with its windings will take place in place of a resistors. So when an alternating current, a simple AC circuit is drawn here with the only supply thing is here will take is an inductor. Okay, so this has a self inductance L. By Faraday's law, it induces an EMF by itself, which is called self inductance, represented by L. So the AC supply has a potential difference V, and we all know that potential difference is given by Vm sin omega t. Here there is a current flowing through the inductor. Because of this alternating current, the potential difference at any point is given by Vm sin omega t, and this potential is between these two terminals. Vm is the maximum amplitude of the alternating voltage, that is oscillating voltage. So this is a simple inductive circuit. So the resistance, in the previous video we have seen what happens when an alternating current is given to a resistor, and the resistive circuit behaves like a current voltage indicator when it is given with alternating current, and there is no time lag between voltage and current in the resistive circuit. Here in the inductive circuit, what happens to the current flow when there is an alternating current is supplied? We all know from Kirchhoff's second law, all the potential differences, all the EMFs across a closed circuit is equal to 0. In that sense, we write the equation V minus, here this is L d I by dt. This has come from the Faraday's law, and this negative sign is comes from the Lenz's law, is equal to 0. So here we write V is equal to L di by dt. Okay, so here the terms will be exchanged to find out the instantaneous current in the circuit. We will write di by dt is equal to V by L. Here V is nothing but, we know V is equal to Vm sin omega t by L. So here multiplying on both sides, left hand side and right hand side, with dt, this becomes di is equal to Vm by L sin omega t dt. So integrating on both sides, because this is an instantaneous current and we have to calculate the current between a full cycle, one cycle of current, that means between the limits 0 to t. Here if you integrate the terms, this will be taken as V by M by L sin omega t dt. So here the integration terms will be I is equal to, see this will become Vm by omega L, and this is minus cos omega t, right? So I is equal to minus we will write here I is equal to minus Vm by omega L cos omega t. Okay, so we know that minus cos omega t by trigonometric functions minus cos omega t, we can write it as sin omega t minus pi by 2. So in here what we will put, I is equal to V m by omega L sin omega t minus pi by 2. Okay, so here this term we can equate for Im. Okay, from this what I can write, I is equal to Im sin omega t minus pi by 2, where Im is equal to Vm by omega L. Okay, so this is nothing but came from Ohm's law, where V is equal to IR. So this omega L is nothing but called inductive reactance. So inductive reactance is nothing but just like the resistance in a normal resistive circuit. Just like resistance, it also opposes the current in the circuit. So if you take the inductive reactance as XL, that XL is equal to omega L, and we can write this I m. See here, I is equal to Im is equal to Vm by XL. Okay, where XL is the inductive reactance. Because of this resistance, which is called inductive reactance here, the current will be lagging behind the voltage. This is the phasor diagram representing the current and voltage. I have given the description of phasors in my previous video already. So if you observe this voltage and current, which are exactly having a phase of pi by 2, and at the instance of time t1 the angular velocity, angular frequency is omega, and this is the way they actually rotate. So you can observe that current is lagging behind the voltage with a phase of pi by 2. That means if you take in the terms of cycle, it actually behind the voltage by a cycle of t by 4. Okay, so that means quarter cycle. If t is the time period, then t by 4 is the time in which the current is lagging behind the voltage. We all know that omega is equal to 2 pi by t. Okay, so t is equal to 2 pi by omega. So the current is lagging behind the voltage by t by 4. That means if you put t by 4 in place of t, this will become 2 pi into t by 4. See the angular frequency, what will be the angular frequency if you put t by 4 here in place of t by 4 here, this will be 4 omega, and 2 will be cancelled, that is pi by 2 omega. Okay, so this is how the time is behind the current is behind the voltage by a time period of t by 4. That means quarter cycle. What is a full cycle? If you observe these rotations, this is the phasor diagram. A phasor is nothing but a rotating vector. This voltage is a phasor and this current vector is a phasor. The vertical components, see, if this is a vector, this is the vertical component of voltage. If this is a current vector, vector means this is current phasor. This is rotating vector is called phasor. This vertical component of this current phasor is gives, see, Im sin omega t1 minus pi by 2 gives the instantaneous current at a time t1 behind the voltage. This vertical component of this phasor will actually gives the instantaneous voltage at a particular time t1. This is the phasor. So when you draw this motion in a sinusoidal curve, that means in a graphical picture, actually you can see this is pi, this is 2 pi and this is omega t is the phase difference, right? So here see, the current is behind the voltage by a difference of pi by 2. You can see this is the difference pi by 2 and here also it is lagging behind the voltage by a phase of pi by 2. So here you can see that the current is decreased, the voltage is higher, current is lower because of the inductive reactance always opposes the current in the circuit. So this is how the inductive inductance circuit is understood. Okay, and we know that the average power consumed, we all know resistance will consume power, right? So when the power is dissipated, that means power is also consumed. Whenever there is a power consumption, the dissipation of electrical energy wastage is also there. So here we calculate whether the inductive circuit has also some power consumption. For that we need to have this formula P is equal to IV, the power dissipated, that means power wasted. If something power is wasted means when it is consumed only some power is wasted. So IV, here I is equal to Im sin omega t minus pi by 2, here V is equal to Vm sin omega t, right? So Im, this is minus cos omega t Vm sin omega t. So by this we can write Im Vm by, I will multiply the numerator and denominator with 2, then this becomes, see, this becomes 2 sin omega t cos omega t and we will put a minus in front of this. So what happens, this Im Vm by 2, this is sin 2 omega t as per the trigonometric formula. Sin 2 theta is equal to 2 sin theta cos theta. So if you take the average power, why we are taking the average power? See, the power supplied in one cycle, see the current in one cycle, average current or average voltage in one cycle is 0. We already did this in the previous video with resistor. So when we take the average, this will be taken into a term like this. This represents the average power. Okay. So here this term is 0. We already proved in the previous video. Sin 2 omega t is 0. So average power is equal to 0. The power consumed is 0. How is power consumed 0? There is a current flow, that means the average power is 0. Here we will see how the power consumption is 0 in an inductor when it is connected to an alternating current. So first one, see, we will see the cases when the current is increasing and decreasing. When it is again increasing in the negative direction and again decreasing in the negative direction. This is positive side, this is negative side. When in an inductor, what happens when the current is increasing from 0 to maximum and maximum to 0 in the positive side, and from 0 to maximum and maximum to 0 on the negative side. So what happens? See, we have taken a core and there is some coil wound on this core. We will see that when the current is flowing like this in the direction, okay, according to right hand palm rule, the magnetic field is generated like this. So we can take the north pole here and south pole here. The magnetic lines will be drawn like this. When the current, this is on the positive side, when the current is on the positive side, the current, say in the half of the cycle, quarter cycle, this is the quarter cycle, the current is increasing, that means current is positive and the voltage is also positive. Because the current is increasing means, as per the Faraday's law, on the positive side the voltage is also increasing. So power consumed is positive, there is power consumption, okay. And on the negative, see the next quarter cycle, in the same way it is decreasing. So the current is positive, see the current is decreasing and it is on the positive side. So here the current is negative, see current is positive, and the voltage, because of Faraday's law, we know that V is equal minus L di by dt. This current is decreasing, that potential difference is negative. So potential difference is negative, okay. So this will be giving back, that means consuming power, and the power consumed here is returned to the source. So all in all, in one cycle the power consumption is 0. In the same way, if the current is reversed here, in the same coil, if you take the reverse current, that means like this. So the current, see the current will be flowing here from, this is say A, this is B, from B to A, okay. Now here the current is in the reverse direction, in the negative side. This side, I am talking about this side, increasing, negative side and increasing. So the current is negative and the voltage is also negative, because voltage is also on the negative side. So the power IV means negative, negative will be, power is positive. So the power is consumed from the source. So when it is decreasing, the current is decreasing in the negative side. Current is decreasing on the negative side. So the current, see when it is decreasing and already on the negative side, so what happens, this is negative, and the voltage on the negative side and the current is decreasing, so this will be positive. So the power will be negative and the power is given back to the source. So on an average, power consumed equal to power given back. So the total power consumed will be 0. So this is how we understand the process of the current and voltage and the power consumed in case of an inductive circuit. So this is the way we should proceed in case of a capacitor also. That capacitive circuit which we place a capacitor in place of an inductor, that we will see in the next video. Thank you.